So whenever you go back in time or go to different cultures, then you realize that people kind of conceptualize the mind, cognitive processing, and its relationship to the body and the environment in very different ways. You need some extra ingredient, according to Searle. Mere computation isn't enough. But instead had a system which could move around the world and could interact with cats, probe cats, see cats, pick up cats, and those kind of interactions were appropriately paired inside that system with certain symbols.
Hi everyone, welcome back to the Embodied AI podcast. You just heard the voice of Mark Sprevak. Mark is a senior lecturer in the School of Philosophy, Psychology and Language Sciences at Edinburgh. He's interested in the philosophy of computation and cognitive science, and I'm very excited to unpack these topics in a second. But before that, you might have noticed that the music in the background has changed. Thank you to my dear friend Plato for creating this awesome soundtrack for me. So for starters, you probably don't think that a stone does computation. But for the unlikely case that you do think that, Mark will in a few minutes tell you why you shouldn't think that. Next, we do some mental time travel and talk about cognition in ancient Greek. And then we discuss the ideas of extended cognition, functionalism, and some takeaways for current researchers doing deep learning. Then, Mark and me get onto the famous Chinese room argument, where we bring up the robot reply and cats. And if you remember the frame problem from episode 1, we revisit this idea by discussing the work of Hubert, Dreyfus and Heideggerian AI. Finally, we talk about Mark's work on predictive coding, which is super interesting and is also relevant for the next 2 episodes coming out. I'll say a bit more about that at the end of this episode. As usual, if you want to skip ahead to specific questions, there are timestamps in the description. Enjoy. Hi Mark, it's great to have you here. What got you interested in the computational theories of the mind?
Thank you very much for inviting me. And it's a pleasure to be here and to have a chat. I've always been interested in computers ever since I was a very young child. I was having lots of fun programming a BBC Micro. And I don't know, there always seemed to be something kind of magical about computers. So you can do sort of really, absolutely extraordinary things with fairly meager physical resources. Quite apart from all of the, kind of fun engineering details, that sort of feeling of being able to accomplish something incredible, magical, just by issuing a few instructions. And that's kind of never really left me. I think one can't help feeling that perhaps our brains are using kind of similar kinds of tricks to pull off another kind of spectacular performance. So, the kinds of things that we do in reasoning and cognition and vision and so forth, that maybe they're leveraging a similar set of impressive tricks. So that's kind of what an initial interest in computers and the feeling that, computers are just marvelous devices has driven me towards thinking about and kind of studying computational kinds of cognition.
That's awesome. Yeah, being interested from such a young age. That sounds really good. So this is a bit of a difficult but also fun question. Does a stone do computation?
Yeah, great question. So I'm going to give you a sort of typical philosopher's answer, which is that in a sense it does, and in a sense it doesn't. Just to give you a little bit of background to this. So there's a debate about what it means for a physical system, be that a stone, be that a brain, be that an electronic computer. So what it means for a physical system to implement a computation. So what makes the difference between the things in the world that compute and the things in the world that don't compute? It turns out to be actually really hard to give an answer to that question. So very smart people have worked on it. There's a big literature on it. Currently in the process of writing a book, which in part tries to answer that question. For the folks involved in that debate, there seem to be some kind of rules on what counts as a good answer to that question. Some of the rules are that, there's certain systems physical systems which clearly are not computational, which are not computing, such as brick walls or stones. Those just aren't computers. And then there are other things which, clearly are paradigmatic examples of computers, such as electronic PCs, or arguably for some people, brains. My view is that what systems compute and what systems don't compute isn't entirely an objective, context-independent matter of fact. So in the right context, even a system like a stone can count as computational. And there are kind of weird interpretations that you can adopt of the physical states of the stone that will allow the stone to do computational work for you. So under the right circumstances, so given the right set of interests, given the right context, stones can be computers.
I think that when I read your work, you might pick up on work of, like, let's say, Hilary Putnam and his Rock, which is doing maybe computation, or John Searle's Wall, that might instantiate a word program in one moment. But I think the key point you just highlighted is that, well, it has to do so reliably.
That's right. So what Putnam and Searle showed, or Putnam did in a kind of a clearer and more constructive way, is that you can basically take any physical system that you like, and if you look at it in the right way, if you interpret its physical states in the right way and the evolution of its physical states over time, then you can get it to perform any computation you like. So you can read any computation into pretty much, there are certain limits, but not many. You can read any computation into pretty much any physical system you like. There seems to be a mismatch between that and the fact that, we only attribute computations to certain physical systems and not other ones. So we don't generally think that computations are very incredibly plentiful in the world. So we don't take brick walls and chairs and tables as computing. So what is the explanation for that? So the explanation is that, according to my view, whenever we say that a system computes, we have to apply a certain interpretation to the physical states of that system. So we might interpret, say, voltages inside a semiconductor device, which are kind of near 5 volts. We might interpret those as all mapping to a certain symbol, the symbol 1, and voltages, which are kind of low, all clustered around 0, is mapping to another symbol 0. But there are all sorts of other interpretation schemes one might adopt. And what Putnam and Searle do is that they suggest that there are all sorts of kind of very, very complicated and kooky interpretation schemes that will allow you to read computations, allow you to read Microsoft Word into the physical activity of a brick wall. My claim is that we aren't free to choose just any interpretation scheme that we like. Whenever we assign computations to physical systems, we are implicitly endorsing a particular subset of interpretation schemes. And relative to those interpretation schemes, brick walls and stones don't count as computing. But there might be, we might have adopted a completely different interpretation scheme, or an agent who had different cognitive abilities to ours, different minds. They might find other ways of interpreting physical systems as perspicacious. So they might adopt different interpretation schemes, different schemes of mapping physical states in that system to abstract computational states. And for them, walls and rocks may function as very useful computational devices. So I hope that's a bit. So as I said, I'm in the process of writing a book on this, but I hope that's a bit clear. So the interpretation schemes that we adopt are tailored to our interests, the kind of physical states that look salient to us in the system, and the kinds of physical states which we can easily manipulate and control and kind of engineer stuff around. And things like physical states inside a rock or physical states inside a wall aren't generally the kinds of things that kind of jump out to us as either salient or things which are easily under our control.
That was really well explained. So let's go a bit further back in history. You're the editor of a book series about distributed cognition, and I'll ask you to explain that in a second, what that is. But it's basically 4 books with an introduction by you and the other editors, and lots of essays on distributed cognition in different time periods in Western Europe. And the 4 books are about distributed cognition in the classical antiquity, distributed cognition in the medieval and Renaissance culture, in the Enlightenment and Romantic culture, and in the Victorian culture and modernism. And before we sort of talk about those time periods or examples of distributed cognition, introduction, you explain distributed cognition with the 4E model. And those 4E stands for embodied, which is, well, this podcast, embedded, extended, and active. And these 4 different terms all maybe fall under this category of distributed cognition, but they mean different things. And I was wondering whether you could unpack the 4 terms for us and maybe with some examples.
Yeah, I'll give it a go. There's a lot to say here, and there are lots of folks who are doing excellent work unpacking what these things mean. So this isn't something which is kind of settled in the literature, but here's my quick take on it. So embodied is really trying to capture the idea that the body matters in some sense to cognition. Now, there are all sorts of different ways of unpacking that. Different folks have different views on exactly how the body matters to cognition. So you might think that certain information processing tasks might be offloaded to bits of the body. Okay, so certain computational problems get solved in cognition because of the action of different bits of the body. Or you might think that, for example, the body contributes to the kinds of concepts that you have in cognition. So we have certain concepts of space and containment because of the structure of our bodies. You might think, so the reason why this is relevant is that if you have a cognitive system which has a radically different body to us, then on this kind of embodied view, you would expect that its cognitive processing would be, or its cognitive states, representations would be really quite different from ours. And arguably, if you had a system which doesn't really have a body at all, and some sort of disembodied AI, then you might wonder whether it can support cognitive processes or cognitive processes in the full sense that we have them. So the second E is the embedded E. We take the body on board now, and now we're saying that it's not just the body which matters to cognition, also the environment matters to cognition. Again, there are all sorts of different ways of unpacking this idea, but kind of a popular one is the thought that we offload certain information processing and information storage tasks to things in our environment. So there's a kind of a classic paper in this area is the Ballard and Rao paper, which looks at how people solve a kind of a puzzle matching task. So they have to copy a pattern, a colored pattern, using shapes. And what they found is that people don't seem to store the target pattern that they have to produce in their head. Instead, they store all the information about the target pattern in the template that they're given, which shows what they have to copy. And they just glance backwards and forwards during the task while they're copying it. So what the people seem to be doing there is that they're using a resource in their environment, an external resource, in order to help them solve a cognitive problem. So embedded is the general idea that perhaps in all sorts of ways which we're not aware of, the environment matters to our cognizing. So if you have, again, a cognitive system, say a disembodied AI, which is kind of sitting in a PC like a HAL 9000 type thing, then perhaps that kind of system wouldn't be suitably embedded in order to display the kind of cognitive processes that humans seem to be capable of. Okay, so that's two E's. Third E is extended. So this is getting a bit more into the distinctively kind of philosophical, metaphysical territory. Generally, folks have taken on board embodiment, that the body matters. They've taken on board the embedded idea that the environment matters, and they make an extra claim, which is that not just cognitive processing uses resources in the environment and it uses resources in the body, or it depends on the body. Our cognitive processing actually literally extends into the body and into the environment. So cognitive processes are not just brain processes, they actually extend outside the head and into physical resources in the environment, which might include notebooks and pens and paper and iPhones and things like that. Okay, so this is quite a radical, or is perceived as quite a radical view. And it's one way of trying to make sense of this. So that's embodied, embedded, extended. The fourth one is inactive. So the proposition that's being considered is that perception, action, and understanding are linked together in a way that might not be obvious to us, or that might differ from the way in which people have assumed in the past. The basic idea here in activism is that perception and action, pretty much everything in between, are all kind of bound up in one bundle, and you can't neatly unpick that. So you can't, for example, atomistically analyze our cognitive powers and faculties or reproduce them. So you can't have, for example, an isolated system that just does vision. Okay, so it might do certain things, it might do certain visual recognition tasks, but to actually do vision and to reproduce the similar kinds of cognitive powers that humans have in vision, you need the system to also be capable of action. So you need it to also to be able to move around, and you need it to be able to deploy the results of vision and understanding. So inactivists think that cognition comes as a bundle and can't be broken up atomistically into little parts. Now, it's worth saying, so those are the four. It's worth saying that there are different ways of developing each one of these four ideas. The four ideas are not necessarily in competition with each other. So certain folks endorse combinations of these. And the exact relationship between these ideas is not obvious. So there's lots of good work being written which tries to unpick exactly how these ideas relate to each other.
Awesome. So the book series is about identifying these 4 E's under the umbrella term distributed cognition in different time periods. And as mentioned them, so antiquity, enlightenment, Victorian era, modernism, which, because you have been an editor on all of these books, and I guess there have been plenty of interesting essays to read. I just had time to look at a few, but which time period do you think is the most interesting in sort of looking at examples of distributed cognition in society?
Well, it's been really fun. So I've been involved in all of them, but I'm only editor on two of the volumes out of the 4, just because we divided up the work. But I read and commented on I'm afraid all of the essays, and I really, really enjoyed it. And one of the things which I kind of learned from this, as someone whose their bread and butter work is just really looking at kind of current stuff happening in cognitive science. So one of the things I've appreciated about it is examples of really thinking radically differently about the mind. So whenever you go back in time or go to different cultures, then you realize that people kind of conceptualize the mind, cognitive processing, and its relationship to the body and the environment in very different ways from the orthodoxy and current cognitive science. And one of the virtues of kind of looking at the history is that it brings our own assumptions. Some of these assumptions are fairly unreflectively accepted currently. It brings those into sharp relief. So I found that really, really useful. So I learned something from all of the different periods, but I think probably my favorite was the ancient, the kind of classical Greek-Roman stuff that we had. It was primarily because it gives an insight into really thinking quite differently about cognition and upending a lot of the assumptions. So, for example, nowadays, the default assumption is that cognition is individualistic. So it's something that an individual does, and it's an activity which is primarily driven by their brain. And it's the burden, if someone disagrees with that, the burden is really on them to kind of show that what's going to move you away from that kind of radical individualism. In other periods, there's an interesting essay about Greek thought and Greek political decision-making. In those kind of contexts, the idea of kind of group cognitions, the idea that a group might be involved in making a decision process, literally deciding, so not in some sort of metaphorical sense, but literally actually making judgments and holding beliefs and so forth. That idea wasn't seen as radical. So what was seen as radical was that only individuals would be capable of having the relevant belief states and mental states. So I think that looking at examples where assumptions about individualism, possibility of group cognition and so forth is thrown into question, I think it's helpful because it's really approaching the human mind from a kind of a different starting point from the one that we have today.
So I'm from a sociology background, but I'm trying to move into neuroscience, philosophy, linguistics right now. I once wrote an essay in my philosophy of science class about methodological individualism. And I found it really interesting looking at other cultures. There was some stuff about Saharan cultures there was this term called Ubuntu, which was something about the ontology of core being. There wasn't really a word for an individual ontology. And I think it's really difficult because I guess science, you need some sort of methodological reductionism to be able to focus on specific problems. But then it's difficult to draw the line in my mind between the anthropology and the neuroscience.
Yeah, so I think that's a good point. So I think that there are two things going on here. So one is that it's interesting as a kind of historical matter or anthropological matter, if you're studying kind of current cultures, to look at variations in people's kind of folk beliefs about the mind and people's folk metaphysics and kind of how people conceptualize minds. And, that in itself is an interesting thing to study. I certainly wouldn't want to go up and say that, the way in which someone conceptualizes the mind in folk terms 2,000 years ago is on a par with what we're doing today. That's absolutely not the proposition at all. So the idea really is to try to think a little bit about the kind of bedrock assumptions that we make today, which aren't really explicitly justified as such. For example, the assumption of radical individualism, it just has to, the burden is completely on anyone who doesn't accept individualism to shift you out of that position. To look at other cultures and other historical time periods where the burden of proof was a little bit different.
In these 4 books, you looked at distributed cognition in Western Europe. And is there a plan to create maybe another book series or book on distributed cognition or a related concept in a different geographical area? And if there's not a plan, regardless of that, which geographical area would you find interesting to explore?
Yeah, so we would like to do that, and we do have kind of plans at fairly early stage. So our first kind of choice of where to go next would be to look at kind of Eastern cultures, so kind of Indian, Chinese, Pacific cultures, and again, absolutely huge range of things to explore there, but having a look at their the ways in which they conceptualize the mind, and in particular this question about embodiment and distributed cognition, so how they thought about it over time.
Awesome. Yeah, that sounds really interesting. Let's now talk about functionalism and computation. We earlier talked about the 4 E's, and one of them is extended cognition. And your most cited paper, which you wrote in 2007, kind of discusses extended cognition and functionalism. And before we talk about that paper, we should probably talk about where this idea comes from. It's from Andy Clark and David Chalmers. They have this paradigmatic example of Otto's notebook, and I was wondering whether you explain that work and the example to us.
So Andy Clark and David Chalmers wrote a paper in 1998 called The Extended Mind. The idea is that when a human being, or when many of us are engaged in cognition, what we do is we recruit external resources like notebooks and sometimes like our smartphones. Now, it's worth saying at the beginning that nobody's making the kind of the claim that things like notebooks have a mental life of their own. So that's a little bit crazy. So that's not the claim. So in the article, they give a number of arguments for this claim of extended cognition. Folks have been working, so there have been literally hundreds of papers published since, which have been responding to those arguments, trying to develop them further. Now, one of the arguments that they give, I think it's the strongest argument that they give, is an argument based on the background philosophical view called functionalism. So yeah, I can unpack that.
Yeah, go for it.
So functionalism is a very widespread view about what it is for any system to have a mental process. So the thought is that in order to think or to reason or to have a belief, it doesn't really matter what you're made out of. So you don't need to be made out of carbon and proteins and so forth. You don't need to be have a brain made out of neurons. So it's not the physical stuff that matters. What matters is that you are a system which has certain internal states which play the right functional role. Okay, so that they are have the right kind of causes in terms of what sort of inputs to the system, what sort of sensory inputs would cause those states to appear, and they have the right kind of effects in terms of what kind of behavior it would drive, and they have the right kind of relationships to other internal states the system might have. So this is a background view which is regarded by many folks in philosophy as kind of the best view we have about the nature of lots and lots of aspects of our mental life. Okay, so essentially what Clark and Chalmers do in that article, or one of the things they do, is to say that if you believe this, so if you're a functionalist about mental life, which many people are, then you should think not just that brains are part of the realization of these physical realization of these functional processes, but also some of the external stuff happening in the environment is as well. And they give a little thought experiment. Their thought experiment involves two hypothetical characters, Otto and Inga. So Inga is kind of a normal human subject, and Otto suffers from kind of a mild version of Alzheimer's. So it's difficulty remembering things. So he always writes things down in his notebook. So one day, Inga hears of an exhibition which is on at the Museum of Modern Art in New York. She thinks for a moment, recalls from her memory where the museum is, and then off she goes. On the same day, Otto also hears of the exhibition, and he opens his notebook, sees where the address is, and off he goes. Now, what Clark and Chalmers claim is that in these two cases, the correct thing to say is that the agent knows or has a belief about the location of the Museum of Modern Art. It's just that in the case of Inga, that information happens to be encoded in some of her neural activity. And in the case of Otto, it's encoded in a resource which is partly outside of his head. But the way in which that resource, in either case, is driving their behavior the way in which that resource is modified as new information might come to light is relevantly similar. So it plays the same functional role. Therefore, if you say that Inga has a belief about the location of the Museum of Modern Art, then you should also say that Otto has the same belief.
Right. So you just mentioned that functionalism is going beyond the physical implementation. And I think in the paper you argue that a limitation with functionalism is that it is then once you don't talk about the specific implementation, you have this debate of how fine-grained you have to be, how much detail of how should mental functions be maybe abstracted or divided into details, and highlight this idea of like a grain parameter of thinking about how much should we go into detail. And I was just wondering whether you could talk a bit about that.
Yeah, sure. So the way in which lots of folks responded in a hostile way to this argument was to say, well, look, these cases of Otto and Inga are really not that alike at all. So for example, in the case of human memory, it has certain characteristics in the way that it decays over time, and that doesn't apply to stuff which is written down in a notebook. Okay, so it doesn't change over time in the same way as information stored in human long-term memory. And for human memory, there are kind of recency effects. So if you learn something recently, then you find it easier to recall. And again, that doesn't really apply analogously in the case of the notebook. So people have said, well, look, I'm a functionalist, okay? Functionalism is correct about the mind, but Inga and Otto are not functionally alike. So the notebook and whatever biological resource in Inga's head is storing that information, they're not playing the same functional role. And they might get them to the museum, but there are lots and lots of functional dissimilarities between these two cases. So what I did was to suggest that, look, what's happening here is that whenever you characterize the functional role of any given mental state or mental process, you have to make a decision about this thing I call the grain parameter, which is what kind of details you ignore and what kind of details you abstract over, okay? All of our cognition is kind of idiosyncratic. It varies between person to person. It varies across all sorts of different demographic groups in humans. So whenever you're giving the functional role of any given mental state or cognitive state, you always have to give it relative to some setting of the grain parameter. So exactly how much detail do you want to capture about its functional profile, and what sort of stuff can you abstract over and can you ignore? So then the question becomes, in this case, well, what is the correct setting of the grain parameter in this context? Okay, so Clark and Chalmers want to set it very coarsely, so relation to these incredibly broad generalizations about arriving on time, and that's all that matters about functional role, whereas their critics want to set it in a much, much finer grained way. So if it doesn't have recency effects, it's not really human belief or human memory. Okay, so how should we adjudicate this? So what's the correct setting of the grain parameter? So what I do in the article is I say that if you want to argue for extended cognition based on functionalism, you need to set that grain parameter very, very coarsely. And there are good reasons for doing that. Like, it's not just an arbitrary decision. So one of the reasons for doing that is the thought that human cognition could have been different. Okay, so we have certain kinds of recency effects, and those effects could have been different. It could have been that human cognition didn't display recency effects. There are all sorts of contingent factors about human cognition that could have been different. So if you want to characterize what it is to have a belief at all, or what it is to have a memory of a certain proposition at all, then you have to characterize it in a relatively coarse-grained way. And there's a fairly big literature about this that says that if you do it too finely, then you're guilty of chauvinism, because you rule out all sorts of creatures which differ just in incidental ways from humans, just in contingent ways from having beliefs. The problem is that if you set it very, very coarse, not only do you get extended cognition, but you get much more extended version of cognition than Clark and Chalmers have proposed. So you get all sorts of weird consequences about our cognition extending into the internet, it extending into libraries, it spilling out into all of our colleagues and so forth. So if you set the grain parameter really, really coarse, which they need it set at, then you get a version of extended cognition which is so radical that it looks as if it's just getting the facts wrong. It's not capturing useful concepts for us any longer. It erases the boundaries between individuals.
Yeah, I was just I had the thought that going back to Otto's notebook and Inga retrieving the memory from her mind, that when Otto looks through the notebook, I guess that's sort of a question of, well, how quickly does he find this information about where MoMA is located? And I think it links back to this idea of, is there a lookup function when he uses the notebook? Because if it's a lot of memories, he must have I guess, a really large notebook. And how does he quickly find information? And I guess normally people might argue there's nothing, the brain doesn't have a lookup function the same way, let's say, some sort of AI might have it. And I guess that's also quite like an interesting difference on how memory works. And maybe we'll get back to that actually later when we talk a bit about Hubert Dreyfus, or maybe not. Let's see. But I was just wondering, going back to the grain parameter and functionalism. So let's say I was a very practical AI researcher and I didn't have the time to engage with this philosophical literature. What would I have to think about when considering functionalism, or when sort of trying to maybe implement something like a grain parameter in my models? Is there something practical I could think about when doing research?
Yeah, so that's a great question, and it's not something which I've confess I've thought a huge amount about. But I think that one thing that might be useful to think about is, whenever you're constructing a model or building an engineering solution, just trying to think, well, what exactly am I trying to model? So what are the ambitions of my model? So am I trying to, for example, capture human cognition with all of its kind of quirks? Or am I just looking at an engineering solution to a particular problem that may solve it in a completely different way? Now, both of those projects are absolutely fine, but I guess it's useful to be clear on the ambitions of what you're doing. So just to be perhaps reflect a little bit on to what extent, for example, your engineering solution, your AI solution, diverges from the way in which humans do it. And in what sense you might claim, or you might not claim, that your model, your AI model, provides any sort of insight or model of human cognition. So the grain parameter matters a huge amount for that. So if you set the grain parameter really coarse, then you can say, yeah, it's my vision system is doing something which is, it's just like a human cognitive capacity, because it's matching human performance across all of these different cases. Whereas if you set the grain parameter really, really fine, then you might say, well, it's not providing a model. What this, with respect to that fine setting of the grain parameter, it's not providing a model of human cognition, because it's not capturing some of the more fine-grained features, fine-grained functional profile of human cognition. For example, it might be susceptible to different kind of illusory cases, or it might be misled under different kinds of circumstances. So I guess when you're making any kind of claim in AI that a model is providing some sort of insight or some sort of enlightenment about how human processing might work, always have a caveat about how you're understanding the grain parameter in that context.
Awesome. You mentioned the Extended Mind paper by Clark and Chalmers was sort of one of the most cited in the 21st century. But let's talk about the Chinese room argument, which is probably the most discussed thought experiment in the 20th century in philosophy and cognitive science. And the argument was presented by John Scholl in 1980. And could you briefly outline to us what the Chinese room argument is?
Yeah, it's a notorious argument. So almost everyone's heard of it. Pretty much everyone, probably apart from just Searle, thinks it's wrong. So I don't think I've met anyone who thinks it's a, in quotes, a good argument. But it just won't die. So people keep coming back to it, and it's obviously kind of, in some sense, telling us something. So the way that the argument works is to say, well, it targets a specific mental process, which is understanding. Specifically, he picks understanding Chinese. Okay, so let's just say for the moment that is a well-defined mental process. And he says, well, let's see if we can replicate Chinese understanding on a computer. So we take some hypothetical program, run it on the computer, and just in virtue of running that program, the computer has Chinese understanding or displays Chinese understanding. So Searle says that's not possible. Reason why is, take that hypothetical program, whatever you like, give it to a human operator who doesn't understand Chinese, so an English speaker, monolingual English speaker, and get them to work through that program by hand. Okay, so just do every single step of that program by hand. So they'll take in Chinese symbols, go through a bunch of different steps, and then kick out Chinese symbols at the end. And now to someone looking at those inputs and outputs from the outside, it looked like the system is giving kind of fluent Chinese responses. But the person inside who's actually implementing the computation is just, from their point of view, is just symbol shuffling. They are not instantiating Chinese understanding, according to Searle. So Searle says that on the basis of this kind of thought experiment, you can conclude that merely running a program, which is in some sophisticated version of symbol shuffling or moving numbers around, merely doing that is not sufficient for a particular mental process, in this case, understanding Chinese. You need some extra ingredient, according to Searle. Mere computation isn't enough.
Yeah, I feel a bit bad because I know you have written a review article about the book Views on the Chinese Room. And also in that book, it was sort of said, well, most people disagree with Searle, and the best thing would be if the argument sort of dies out. And in the review article, you also mentioned that it's maybe not best to look at argument from an interdisciplinary perspective because it's interesting for different disciplines, but if one tries to narrow the argument instead of broadening it, then maybe it's easier to see some of the flaws of it. And I'm just bringing it up here in an interdisciplinary podcast, so that's not great. I'll just keep it alive. But I was wondering whether you could talk a bit about this idea of Searle that syntax is not sufficient for semantics, because that is sort of like a point he's trying to make with the argument.
Yeah, so he has this slogan that syntax is not sufficient for semantics, and it's worth bearing in mind that he means something relatively specific by syntax. There also something relatively specific by semantics as well. So what he means by syntax is the kind of symbol shuffling that the system undergoes, so the kind of formal manipulation of formal symbols. So he had in mind so this isn't to do with syntax in the linguistic sense about well-formed sentences and so forth. It's more about manipulating formal symbols just in virtue of their form or symbolic type. Now, this doesn't just apply to kind of the classical symbol systems. Like what he has in mind as well is also manipulation of kind of formal numerical values. So, for example, in a connectionist network, you might have a matrix of connection weights, or you might have a set of activation values. So he also means that syntax would also include the rules for formally, modifying those numbers in response to numbers which are coming into input nodes. So it's the kind of the formal manipulation process that defines the computation. That's syntax. Semantics, in his view, there is really primarily about reference. So it's not necessarily mapping onto semantics as it appears in computer science and AI. It's more about the referential content. So what are those symbols referring to in the world? So you might have the symbol CAT, and you might have various rules for manipulating that. And when that symbol appears or disappears, or when it's warranted based on sensory input for that symbol to somehow appear in some internal blackboard system or whatever. So what he means by semantics is the referential content or semantic content associated with that. So the fact that that symbol refers to cats as, real, very physical things in the world. So it seems that humans have inside their heads states which have referential content. So we have representations of the outside environment. We have thoughts about cats. We have dreams about cats. We have images of cats. We have beliefs about the locations of cats and so forth. And these are semantic properties of our internal mental states. And what Searle claims is that no matter what kind of syntax stuff you're doing, manipulation of numbers internally according to numerical rules, manipulation of symbols according to symbolic rules, do as sophisticated stuff as you like, you're not going to be able to fix the semantic content purely in terms of those syntactic relations.
Right. So maybe you can bridge the cats example to the next question. As I said, it's quite like a famous argument, and there have been lots of critiques and responses by Searle. And these points of disagreements have been grouped in different replies. I'm just doing air quotes for the listeners. And one of them is the air quotes robot reply. And I was just wondering whether you could maybe link this idea of the robot reply to the examples of cats to the podcast about embodied AI and maybe externalism? I know it's quite a lot, but I think it all sort of fits together.
Yeah, so I'll do my best. So the robot reply is so Searle considers a number of possible replies and then gives his responses to them. The robot reply is to say, yeah, perhaps disembodied AI system, like running on a desktop PC or whatever, just by running a computation, it wouldn't have the relevant mental processes, it wouldn't have semantic content and so forth. But if you stuck that machine inside a robot or connected it up to sensory interface and some kind of robotic effectors and allowed it to move about in the world and interact with stuff in the world, then it would be able to have understanding. For example, if you had a system which didn't just, as we were first conceiving it, take Chinese symbols as an input and gives Chinese symbols as an output and just kind of manipulate them in between, but instead had a system which could move around the world and could kind of interact with cats, probe cats, see cats, pick up cats, and those kind of interactions were appropriately paired inside that system with certain symbols, with the CAT symbol, then that CAT symbol would come to represent for that agent cats. Okay. So in virtue of its kind of robotic embodied interactions with the world, it would gain semantic content. And there's lots of precedents for this kind of idea. So there's a thing called the causal theory of reference in philosophy, which is an account of how symbols get their meaning. And it says that in order for a symbol to get its meaning, it's not enough for it to be kind of defined in terms of other symbols. You also need certain causal relations to obtain between that symbol and what it represents in the world. So there needs to be some sort of causal connection between them, and the robots potentially provide that. Okay, so that's a robot reply. Now, Searle says two things. He has a very strange thing, and he says in response to the robot reply. And so he says two things which appear contradictory. But I'll try to briefly unpack them. So the first thing he says is, the robot reply is right. I got you. So if you accept the robot reply, or if you go for the robot reply, then you've admitted that mere computation alone isn't enough for understanding or for semantic content. You need computation plus the right causal relations. So you need computation plus interacting with the environment in the right way. And that interaction, that causal interaction, is non-computational. So it's characterized purely in causal terms of interaction with specific physical types. So he says, well, look, okay, you've basically admitted that I'm right. Computation alone isn't sufficient. Then he does something else which is kind of weird that nobody's really kind of fully unpacked, which is to say, well, the robot response still doesn't work. And his idea there is a little bit more speculative. The way I've understood it is to think of it as saying, well, look, I might start off with the robot reply, but I might say, no, I don't want to concede this stuff about causal relations. What I'm going to say is that the robot would be sufficient, but having just a virtual environment would be sufficient as well. So what I could do is, instead of having my embodied robot interacting with real cats, I could just run the whole system on a PC, disembodied PC, in a virtual environment, interacting with virtual cats, and that's enough for it to acquire, for its symbols, the symbols inside that system to acquire meaning that they get to refer to either the virtual cats or the real cats or whatever. But you can do it all without actual physical interaction. So Searle has a big argument where he says, no, that won't work. Because he says, well, you can just imagine the man inside the room running through the symbol manipulation for all of that. So taking in perceptual symbols, manipulating those perceptual symbols, and then giving kind of motor symbols or motor commands as outputs. So he has a kind of extended argument, which I think is probably the charitable way for understanding it, is an argument against kind of virtualizing the robotic interaction and showing the importance of actual physical stuff.
Okay, now let's talk about your intellectual take on the argument. So you have written about it in 2007 and in a forthcoming paper titled Philosophical Issues in Computational Cognitive Sciences, which I want to get back to in a second as well. But what is your take on the argument?
I think the reason why the argument is so compelling is that it says something which is, I think, very reasonable and also simultaneously seems completely outrageous and mad, okay? So the reasonable thing that it says, which I think actually the vast majority of folks, even in Searle's time, would have agreed with, is that mere symbol manipulation alone isn't sufficient for having a mental life, for having semantic content. So lots and lots of folks have been saying that in all sorts of different forms for a long time. So this is sometimes known as the kind of the symbol grounding problem, that, if you just have your symbols defined in terms of other symbols, you're never going to get out into the world and get to refer to stuff. So you need something beyond that. And I think that a lot of folks working in the AI paradigm would be happy enough to accept that, and would assume that, that's already baked in as part of the proposition for what AI would look like. Of course, it's going to have some interaction with the world. It's not just a purely formal system existing in a vacuum. So that's the reasonable thing that it says. And I think the thing that it does get right, and the thing which I think is valuable about the thought experiment, the thing which is a little bit mad is to say that no possible AI system would have understanding. And that seems a bit mad because we just haven't explored the full range of possibilities.
Right. I just mentioned the paper, which is forthcoming, Philosophical Issues in Computational Cognitive Sciences. And within that paper, besides the Chinese room argument, you talk about the frame problem. And this came up in my first podcast episode with Ron Chrisley. But I just wanted to ask, could you sort of remind us what the frame problem is before we go into follow-up questions?
So lots of folks have written on this. So Daniel Dennett, Jerry Fodor, more recently Richard Samuels and Susan Schneider and Kurt Ludwig have all written trying to precisify, trying to say a little bit more precisely exactly what the problem is. And I don't think anyone has kind of really neatly pinned it down yet. So that's work which still remains to be done. But there is general consensus that there is a problem in this vicinity, even if it's difficult to exactly formalize it. So I'll do my best to say what I think it is in informal terms. So it arises specifically in open problem domains. So in domains where you're doing kind of general purpose reasoning, you're trying to construct a general purpose AI system. So systems which aren't tailored to solve one particular task. So where the problem isn't clearly defined for the system. So general purpose systems. So what the frame problem, or what people refer to the frame problem is a problem that any such system is going to have to solve if it's going to take action in any context. And that problem is to work out what is the current problem it's facing, what is the specific problem. So for most AI systems today, they're special purpose. So that's hardwired into them, that's engineered into them. So the designer has usually made some assumption about what task the system is going to face and what it should optimize for. But for a general purpose AI system, you can't hardwire that in or engineer that in. The system might be facing any number of different tasks, and it has to work out in any given context. It has to recognize what the context is, what it should be optimizing for in that context, what things to ignore, what things to prioritize, and how to manage its time resources. So how much time can it devote to thinking? How should it balance acquiring more information? What sort of features to detect? So if it's doing some sort of visual task, what sort of features should it be tuned to pick up, and so forth. So all of these are kind of decisions which are often made either wholly or at least in part by an engineer who's designing a special purpose AI system. But for a general purpose AI system, it needs to make those decisions itself. And how does it do that? So how does it solve that problem of working out what context, what frame it's in, what's appropriate, what should it be doing? Well, that seems to be a similarly kind of open and unconstrained problem for it to solve. So the typical solution, the kind of the simple-minded idea might be that it could perhaps search in some way through a bunch of different alternatives and see, is the situation matching one of any number of different alternatives? So is it one like this, like this, like this? So is it, an instance of this problem, or this problem? And the problem is that if it's doing any kind of search, it's going to have a huge range of options to search through. And it's not going to have any kind of constraint to do that, because it's not going to know sort of what's relevant what sort of features are relevant in the search. It's difficult to know what exactly is the nature of the argument. So some people seem to present the argument as we've got reasons to think that no possible computational system will ever be able to solve this problem. Being able to work out what the context is beyond all computational power. It's quite difficult to make the case for that. So there are certain people who've done that. So Jerry Fodor is one of the people who've argued there's no possible process which would be able to do that. There's another way of reading the problem, which is just that it's a description of the difficulty of creating general purpose AI. So it's just saying that a challenge, if you want to create general purpose AI, is that you have to have a system that recognizes any number of different problems and is able to kind of flexibly adopt them and switch between them, depending on what's relevant in a given context.
Yeah, just to also give an example, and I'm totally stealing this from you from the paper. You mentioned this example of, let's say there was an agent and he has to understand when he does the function eat the object sandwich, this does not change the position of Australia. And that makes sense for us. But basically you made the case that somehow the system needs to implicitly encode that without going through that search function of, well, oh, do I have to care about content positions and all of that? Let's talk about Hubert Dreyfus. And this question is quite important to me because actually this is his argument sort of motivated the idea for the podcast. So I'm really happy to talk about this. Hubert Dreyfus has criticized symbolic AI a lot and recently also connectivist. In his response to the frame problem, he sort of highlights the role of embodiment, but also says that symbolic AI and to some extent connectivist AI can't really solve the frame problem. And could you sort of summarize his argument for us?
I think that the way in which he puts it, at least in the instance from which I had in mind, was about the AI system not. So again, going back to the characterization I gave earlier about it, trying to work out what the current context is. So the thought is that we humans are always operating within a given context. So whether we're, tidying away the dishes, or we're answering our emails, or we're walking through a door, or whatever. So we're always aware what the context is and what kind of information is relevant and not relevant. An AI system needs to somehow work out a general purpose AI system needs to work out what the current context is for any given action. And it's not clear how it's able to do that. So if you just give it lots and lots of data about the world, so you tell it lots and lots and lots of facts about the world, so you give it encyclopedic knowledge or encoding of everything. So what Dreyfus originally had in mind was the Psych project, the Doug Glennon Psych project, which was to try to encode all of human common sense knowledge inside the AI system. And then once it has that, then it should be able to do full general purpose reasoning and work out what's relevant, what isn't relevant. Dreyfus's point is that you're just kind of dumping more and more data on the system, and the system still doesn't know what's relevant and what isn't relevant in that data. Now, Dreyfus had in mind the challenges faced by a symbolic reasoning system operating over that data. But similar problems are going to arise on kind of deep learning or connectionist systems as well. So those systems as well, the data is curated and those systems are engineered with various hyperparameters to identify stuff which is going to be relevant and not relevant. It can work out some degree of relevance by itself, but there's a lot of stuff, for example, in visual systems doing feature detection. There's a lot of engineering which is done kind of outside the system to try to kind of bias it towards detecting certain types of features and not other types of features. So how do you get a system which is able to kind of flexibly switch between different kinds of tasks and be attuned to different things in its data being relevant for different kinds of tasks? So that's still something which I don't know how to do. It's an open problem.
Awesome.
I don't know if that fits with how your reading of Dreyfus.
I mean, I have to be honest, I've only read the book What Computers Can't Do, but I think the focus on the common sense database and trying to navigate within that, I think that is the main point. I guess a follow-up would be, which I guess links slightly to embodiment. Dreyfus developed this idea of Heideggerian AI, which comes from the philosopher Heidegger. And he has written about that. And I know you have worked together with Michael Wheeler, who has also written about this. And I was wondering whether you could maybe say a bit more about that, maybe link it to connectivist deep learning, some of the challenges they might also face from those arguments. Maybe you can link those.
So the idea here is, this was a proposed solution to the kind of problems that were posed by the frame problem. And it took its inspiration in part from kind of Heidegger philosophy stuff, and in part from the Rodney Brooks kind of embodied robots, simple robots type stuff, embodied cognition stuff, and kind of married those two ideas together. So the basic thought here is that, look, this problem of context determination, it's not solved by us just inside our brains, just by kind of churning away on the data, the sensory data, and drawing on our beliefs, and then kicking out an answer. Okay, this is the context I'm in. This is the current problem. Let's get off and let's start solving it. Instead, the right way to see it is that the context determination problem is solved in part by the particular relationships that we have to our environment and the way in which we typically find ourselves involved in certain actions in certain environments. So it's not done necessarily entirely computationally. It's partly done by our embodied action in the world. So things like, the world is its own best model in certain cases. So going back to the stuff which I mentioned, like the nice paper by Ballard and Rao on copying patterns by storing information out there in the world and just looking at it. So that's fairly well supported. The thought that this kind of approach is the answer to the frame problem, I think that is something which is still a bit of a promissory note. If Heideggerian AI was able to neatly solve this, then we would have done so by now, and we haven't. So it's an active research program. It's something that possibly AI researchers working on AGI might want to consider, that, if they're trying to build an AGI system, don't just try and build an entirely disembodied system. You need a system which is going to be interacting with the environment and with human agents and moving around and so forth, and is able to have kind of a fairly rich embodied interaction. And it's going to need that in order to help it determine what context it's in.
Awesome. Let's move from the idea of how we can use embodied robotics to how we can use neuroscience for AI. A really popular paradigm in neuroscience right now is predictive coding. And I think there's some interesting comparisons with deep learning and reinforcement learning. You have recently written 4 preprints, which I assume will be soon published. And before we kind of talk about what predictive coding is, I just very like how you structured those 4 preprints. So it's the first paper introduces predictive coding. The second, third, and fourth take the work from David Marr, who has talked about this idea of, he has worked on vision and computational levels, different levels of thinking about the brain. And those 3 levels are the computational level, the algorithmic level, and the implementation level. And then you use those 3 levels to structure your second, third, and fourth preprint on predictive coding. And I just thought, could you maybe talk a bit about these 4 levels?
Yeah, no, thank you. So David Marr's distinction between, so the three levels is usually conceived as the computational, algorithmic, and implementation level. Probably for some listeners are very familiar with Marr's 3 levels, but just very briefly to characterize what they are. So the computational level describes kind of the task description. So it's describing what computation is the system trying to perform. So what function is it trying to compute? Is it trying to add numbers? Is it trying to do a Fourier transform? What's the task it's trying to do? And you might ask the same question. So what Marr did was said, well, let's ask that question of the brain or various bits of the brain. So what is the function of the early visual system? What function is it trying to compute? Never mind about how it's doing it, what's it trying to do? So that's the kind of the black box view of it, and you're looking kind of at the input-output pattern of it. And the algorithmic level looks at the abstract computational process by which it tries to do that. So what sort of steps, what sort of operations does it take in order to try to compute this function? And the implementational level looks at the kind of the physical basis, the physical nuts and bolts that implement that abstract process.
Awesome. I know this next question you could probably talk about for hours, the question of what is predictive coding. So I think I'm going to break it down and maybe first ask, what is prediction error minimization?
So maybe I'll say, maybe it'd be useful to say, I'll say briefly how I split it up in the paper in terms of what the claim is at each one of these 3 levels. So the first level, Marr's computational level, the question is, what's the task that the brain faces, the computational task the brain faces? And according to predictive processing, the brain always faces one computational task and only one computational task, not a million different ones in different circumstances. There's only one. And that task is always to minimize its sensory prediction error. Okay. So that one task description fits all aspects of cognition if understood in the correct way. At the algorithmic level, what's it saying? It has a specific proposal about how the brain tries to minimize sensory prediction error. The particular model it has in mind is a connectionist model. It's quite different from traditional, well, I would say traditional contemporary deep learning systems. So it's very different architecture from those. It's a hierarchical architecture, and it's based around having certain groups of connectionist nodes being labeled as prediction units and error units. Okay, so it has a specific general connectionist architecture by which it says that the brain is trying to minimize sensory prediction error. Then at the implementation level, it's making a claim that that connectionist architecture of nodes and weights and so forth is implemented in certain specific areas of the brain, so namely in the neocortex and in pyramidal cells. It associates certain very specific aspects of neural activity and neuromodulator release with different aspects of the formal model.
All right, so you just mentioned for the algorithmic level that you got hierarchical layers of artificial neural networks and that's quite different to deep learning architectures. Different how?
So it's a good question because deep learning isn't precisely defined what the constraints are on the architecture. So it's kind of a feel for it more than, a precise formal definition of what isn't and isn't deep learning. And similarly with predictive coding, predictive processing. So there's no canonical description of the architecture must look exactly like this. So you can't really say categorically, look, these two things are never going to match up. But they do have quite different feels to them. So for example, kind of a simple form of deep learning, like a feed-forward network, a convolutional neural network, which is very good for image recognition and so forth. It's going to be quite different from that in that with these kind of networks, you've got a huge amount of information flowing kind of backwards towards the sensory input. So there's recurrent flow upwards and downwards. It's divided up into layers, but the layers are quite different from the kinds of layers that you find in deep learning systems, either feed-forward systems or systems which have some recurrence in them. So on weight change, for example, in deep learning, some version of backpropagation is kind of usually adopted. In predictive processing, predictive coding, backpropagation is very rarely used. So it's standard to use a Hebbian form of learning algorithm because it's thought that this is going to be kind of lend itself a bit more to being plausibly realized in the brain. But yeah, it's worth emphasizing that what's meant by, so both talk about layers, but the layers are totally different in both cases. So they're kind of fairly well-defined examples of very simple toy versions of predictive coding, predictive processing. I kind of walk through a very, very simple network that does predictive coding in the paper. But those networks are obviously, in very obvious ways, unrealistic and not good models for any human cognitive process. But exactly how to generalize those networks to make them a bit more sophisticated, that is very much an open question. So there are a number of papers which I cite in the article which look at dozens of different ways of having more sophisticated connectionist networks which are doing predictive coding, predictive processing. I guess the best way to put it is that it's a specific type of connectionist network which has a kind of a different flavor from the kinds of networks that people think of whenever they do deep learning.
Right. So you just mentioned some of these models you discuss in the paper. And I think you got this interesting comparisons between like two groups of authors of how this might look like in the predictive coding algorithms. So comparing the work of Spradling, who published something in 2008, and then Marr and Ballard, who you mentioned earlier. You earlier mentioned these prediction and error units that have connections with them. And some of the disagreement is on whether the complicated structure that is between these prediction and error units that is doing most of the prediction and error work, as to say, whether that complicated structure is within the different layers in this hierarchical layers, or whether it is between the different layers. And you talk about the advantages and drawbacks on both sides. And I was just going to ask, which side would you put your money on if you had to, and why?
Oh, I think it's too early to say. I guess all I was trying to do is to say that, one of the ways in which people characterize predictive processing, predictive coding, the algorithm, is to say that error signals are going to flow upwards in the network, sort of away from the sensory input and up, whereas prediction signals flow downwards, so from the center down to the sensory periphery, and those predictions are used to cancel the incoming error signals. So it's very often said that, this is kind of what defines a predictive processing or predictive coding architecture. Errors kind of go upwards and predictions go downwards. So Spratling has made the point, I think, very, very neatly that, this just really depends on how you label layers within the connections network. So how you kind of draw a circle around a bunch of nodes and say, that's what I'm calling a layer. So you can do that in one way, and then you get predictions flowing downwards and errors flowing upwards. But if you draw the layers in another way, so you just draw a circle around a neighboring set of nodes and say, I'm calling that a layer, then you get the reverse. So then you get errors flowing downwards and predictions flowing upwards in the network. Now, the decision about which nodes we call layers and which nodes we don't call layers, that's just a terminological matter, nothing, that's not some intrinsic feature of the network. That's just about how we label the nodes in the network. So it can't be that what distinguishes predictive coding from other architectures is the direction of errors flowing upwards and predictions flowing downwards, because you can have exactly the same connections network with the reverse holding. So I thought that was kind of a neat point in Spratling's article, and I try to illustrate that in my review. It brings to the fore the need to be clear on what assumptions someone's making whenever you're looking for empirical evidence of predictive processing. So if you find empirical evidence for perceptions perceptual data going upwards in the brain, then that may well be still consistent with the model. So there's absolutely no reason why that isn't consistent with the model.
Awesome. This next question is a bit about this idea of multiple realizability, which is this idea that, different physical implementations might do the same computation, or in this case, predictive coding. And you just earlier mentioned the neocortex, which is a good hypothesis for where that might be happening. But you also outlined the idea that, different areas could also do this with different physical implementations. And I was wondering whether you could maybe also link it to evolution, because I suppose the neocortex is prominent in mammals, but I'm not sure about birds. But for example, with insects, which I talked with Barbara Rapp about in the last episode, she made the case that flies probably do some sort of form of predictive coding, because they need to fly around, and then they need to account for their movement and their vision, and then it basically needs to predict their motor movement to account for that change in the vision. And since they don't have a neocortex, but they might have other structures, what is your sort of take on this idea of physical implementation and computation of predictive coding?
Yeah, absolutely. So this is a helpful way of thinking about the implementation claim. So the implementation claim, as it's kind of standardly presented in the literature, is really something specific about humans or mammals, so at least creatures that have a neocortex. So predictive processing, predictive coding is claimed by many advocates as not just an account of human cognition, but as a general account of all forms of cognition. Like in the strongest form of the view, it's an account of what cognition could possibly be. So any possible form of cognition must involve predictive processing, predictive coding, according to the ultra version of the view. So that obviously means that if you are committed to that, then creatures which don't have a neocortex must be implementing the algorithm in some other way, using some other physical resources. And there's been a little bit of work done on birds. And so birds, at least to my knowledge, don't have a neocortex, but they have certain structures which are claimed to have an analogous function, claimed to be used for implementing the algorithm. I think one has to be a little bit careful here. So this is going back to the very start of our conversation. So brains have a huge amount of activity going on inside them, whether that is a human brain or a bird brain or an insect brain. So there's a lot of different patterns of physical activity going on. And if you're kind of looking for patterns in that physical activity, it's quite possible to read fairly abstract computational structures into all kinds of different physical systems. So it's possible to find instances of the predictive coding algorithm in human neocortex, in birds, in insects, in computers. I think that one of the points I make in the final paper, the implementation paper, is that one has to be very clear on what would count as empirical evidence for the view. So mere consistency between patterns of detected physical activity and the formal model is a very, very weak criterion to meet. So given the richness of physical activity that you're going to find in the brain, it's a fairly weak criterion to meet. So what you've got to really show is that the model is doing significant explanatory work, so it can explain the behavior of that system better than any other competing model. And that's something that is kind of an ongoing project in the predictive coding world, and something that I think folks working in that world need to take really, really seriously, because the standard of merely just being consistent with behavioral data or neural data is actually a fairly low one for such an abstract and unconstrained computational model.
Awesome. This is the last academic question, and then I'll have some personal questions. So another disagreement in the predictive coding algorithm is whether it's representation light or representation heavy. And what is your intuition about this? And before we talk about representation light or heavy, why is representation necessary at all in the brain?
Yeah, well, that's a very big question. Yeah, so I think that default assumption, I think, of most folks working in cognitive science is that there are representations in the brain, and that thinking in that way is very useful for explaining behavior. There are excellent reasons for thinking that there are representations in the brain. There's a lot of disagreement about exactly what those representations are, how they're physically realized in the brain, how they drive behavior, and so forth. Now, there is a camp within cognitive science, and that includes many philosophers as well, who are anti-representationalists, and they think that kind of orthodoxy, representationalist orthodoxy, is mistaken, that there's some massive error in literally attributing representations to the brain. Now, the reasons for that might be various. So they might think that the notion of representation is somehow defective or somehow interest relative, or that it involves taking on this project of naturalizing representation, which is a kind of a project which has been really, really hard to do. So they think that it's better if cognitive science just doesn't talk about representations or doesn't posit representations, and tries to explain behavior and our capacities in a purely non-representationalist way. So that might involve appeal to dynamical properties, it might involve behaviorist dialectic explanations, a whole host of different options there, but just don't use representations. Now, that view is currently in a minority. The reasons why people avert to representations and think that they're so useful is that it's difficult to, like, there's certain cognitive phenomena that can be explained without appealing to representations. So certain aspects of motor control and certain ways in which our body might be able to maintain stability in the face of kind of changes in the environment or changes in our bodily orientation might be explained purely as treating us as a kind of a self-regulating system that doesn't necessarily need to represent, but is just kind of responding in a little bit analogous to the way a watt governor governs the flow of steam inside a steam engine, okay? But whenever you come to try to explain cognitive capacities that require reasoning or inference or deliberation or bringing together beliefs about things which are not physically present, so stuff which isn't there, so this kind of aspect to do with reasoning, thought, and so forth, that's really quite hard to account for in non-representationalist terms. That's kind of the primary thing that pushes people towards positing representations, that there are things which act as proxies, useful proxies for objects in reasoning. So you asked about representation light versus heavy. So there are two versions. There are two ways in which predictive coding, predictive processing is presented in the literature. And it's actually interesting because the view is endorsed by some rabid anti-representationalists, and it's also endorsed by people who are massive fans of representation talk. So the explanation for that is that there's kind of two ways of reading the kind of the mathematical and computational apparatus of the view. So you can read it just as in non-representational terms, so just as describing how the system's going to respond based on certain magnitudes of sensory input, and it's just trying to minimize those physical magnitudes of error signal which are associated with sensory input. So that's a way in which the view is sometimes glossed. Or there's a kind of a probabilistic reading of the view where you interpret these magnitudes which are associated with values in the connectionist network as statistics, like encoding key statistics of subjective probability distributions that the agent entertains, so probabilistic guesses that the agent has about the environment. So that's a way of reading the same computational model in probabilistic terms. So all the numbers in it don't just correspond to physical magnitudes in the system, they also correspond to parameters of subjective probability distributions, which are probabilistic guesses that the agent is entertaining about the environment, which are very representational, at least on most people's understanding of subjective probability distributions that the agent might have. So that's kind of the representation in a nutshell, the representation light versus the representation heavy readings of the view. And the view as a computational framework doesn't decide between these two. It's compatible with both, and different authors kind of might add this representational gloss, and other authors eschew that representational gloss or say that, yeah, we can talk in those terms, but it's not literal and you can just junk that kind of stuff, and we're not really committed to the system having these probabilistic representations literally inside it.
All right, let's do a few career and personal questions at the end. So the first one, this is a bit selfish because I want to do my master's in Edinburgh and you teach there. So I thought I'd ask you, what is your favorite thing about living, researching, or teaching in Edinburgh?
Oh, wow. Well, yeah, I would recommend it. So there's a lot of nice things to say. So there are two great things about being in Edinburgh. So one is totally unrelated to the university or whatever, which is it's just a magical place. It's just wonderful, wonderful place. So there's no kind of accident that, it's J.K. Rowling, is famous for writing Harry Potter here. It has this kind of magical air and a beautiful, beautiful, unique city that's wonderful to live in. So I enjoy that, I have to say, every single day. My walk into work is just a joy. So that can't be discounted. Secondly, it's a really, intellectually, in terms of the university, it's I think a really fun and stimulating place to be. So it's a place which kind of embraces, in general, a kind of a naturalistic, empirically focused, interdisciplinary approach to the mind and cognition. So it's easy to interact with other folks in philosophy, in linguistics, in psychology, in computer science, we call it informatics here, in AI, who are all kind of looking at similar kinds of problems and coming to it from different perspectives. I think it's a really, really great environment for this kind of inquiry. So yeah, I heartily recommend it for those two reasons.
Right, I'm really looking forward to it. So you are a philosopher of cognitive science and computational theories of the mind, and talked about so much today. And I assume you have a lot of philosophical reading, a lot of technical reading in a lot of fields, neuroscience, AI. So has there been a topic or concept you really struggled with understanding sort of conceptually? And how did you manage to better understand it?
Yeah, loads of topics. And I still haven't understood most of them, I'm afraid. So I guess recently the one that stands out to me is the predictive coding, predictive processing stuff. So I wrote these 4 papers and it took a long time to write them. I read a lot of literature. And it is really, really difficult literature. It's very, very, I think, kind of confusing and difficult for anyone. I wouldn't claim to have understood it. I think that it's not a settled matter within that literature what the view is. So it's something which is very much in flux, which makes it difficult to track. Partly it's that I have my own limited cognitive capacities for understanding it, and I've probably misunderstood it. But this is my best take on a simplified version of the view. On how to understand it, I read tons and tons of stuff and just kept kind of struggling to make sense of it, make sure that it's different authors, my understanding, different authors are saying things which are coherent. And the thing which I found most useful, which I did many, many times, is to try and put it in my own words. So I went through many, many drafts. So I think if you're encountering a topic which you find conceptually difficult to understand, I think trying to summarize that topic in your own words is kind of a painful, but probably the most productive route for gaining an understanding or gaining a better understanding of it. That's what I've attempted in my very incomplete and feeble way to do.
Yeah, that does sound really good. I really like writing, and I think it does help me with understanding different things. So relatedly, are there like any reading strategies that you employ if you either have something really complex like predictive coding or really large amounts of volume of reading?
Yeah, again, this is a challenge, and I think it's just a little bit overwhelming now, just how much there is out there and how rapidly stuff is coming out. And it's just, especially if you're working in philosophy of cog sci, because you've got to sort of track the philosophy literature, and you've got to also, try to do your best to track the cog sci and related literature. And it's just so much. I don't really have a strategy for tackling the volume. I wish I did. I'd love to have some advice on that. If there's something which is complex or I don't understand, which is often the case, I found that one thing which is useful is to really go back to basics. So I find actually going to textbooks, elementary readings and elementary guides really, really useful, and to kind of be humble and just start really at the very beginning and get a solid foundation. So I think that often, especially in kind of technical areas of the literature, picking up what's going on by reading the latest articles is not always easy, because authors are often not super clear about what the view is, how exactly the view works, and they might not even be 100% clear themselves on all of those details. Coming to it from an outsider and trying to make sense of the whole thing, it can quickly get really, really baffling. Whereas if you just kind of reel back a little bit and, start working at the very basics with, working through textbooks, working through example sheets, then you're working on stuff which is really, really solid, really well explored, and you're building up a good foundation of intuitions that whenever you then go and look at the kind of the bleeding edge stuff, there's more chance of you understanding kind of what's kind of going on there and what's significant and what isn't significant in the model. So yeah, I would say that, talking to my own students, they often feel like, oh, I don't have time to, read a textbook in AI. I just got to get going and start reading all these articles. But I would say that the investment that you make in kind of reading the very basic stuff just, will pay off massively.
Yeah, I can imagine myself. I should probably do that more, because I do think I read a lot of articles where I then think if I had only got the basics, but more like foundational, that would have made a lot of future work like quicker to read.
Yeah, that's right. It's often difficult when you're reading the kind of latest stuff, if you're not familiar with it, to know what is kind of the solid, like trivial bit, and what is this is really exploratory bit, because it all just shows up as baffling and new and complex to you. Whereas, yeah, if you already kind of know, oh yeah, it's one of those type of models and they're doing this little twist on it, then suddenly the whole thing makes sense. You can better appreciate what the authors are perhaps up to in it.
Yeah. Any final advice you would give to someone interested in doing an academic career in the philosophy of cognitive science and computation?
No, I think it's a very exciting time to be working in this field. And, if I think back to my own time as a graduate student, it was relatively dormant. So it was still the time of, we were still within an AI winter, even though it wasn't that long ago, but AI wasn't regarded as a particularly exciting or promising project in those days. Computational models of the mind were looked at as a slightly skeptical manner. And now it's just kind of full steam ahead in all sorts of different fields. And there's just so much stuff to engage with. In fact, there's an embarrassment of riches now. So I think the problem is that it's difficult to know for someone starting out exactly what they should be focusing on. So good time to get into the field.
Yeah, that's perfect for me. That's great. So this has been amazing. Thank you, Mark, for taking so much time out of your day. This has been really fun. Thank you.
Thank you very much. I've really, really enjoyed chatting. Thank you.
Awesome. I hope you liked the episode. As I mentioned in the introduction, the next 2 episodes will be related to predictive coding. In the next episode, I talked to Baron Millich about his paper on reinforcement learning through active inference. Active inference is sometimes also known under the term free energy principle, and as you will find out, this idea is closely related to predictive coding. And in the other episode, I'm talking to Felix Hill from DeepMind, where we talk about NLP with grounded language models, and I'll ask some questions about prediction as well. To find out when these 2 episodes are coming out, please follow the Twitter or LinkedIn account in the description. Enjoy the rest of your day.